Welcome to the Julius Technologies presentation. We're really excited to be here as a sponsor and Julia advocate. As Ranjan mentioned, my name is James, and I'm the CEO and co-founder of Julius Technologies. And we're a company founded by experts in the fields of computational finance and graph computing. Our team has built some of the most complex data and analytics systems at global investment firms, and we have decades of practical hands-on experience addressing the challenges that engineers typically face when building enterprise-scale pipelines. I can remember back when I was running a trading business, there was a model upgrade that we'd spent almost a year working on that produced wildly erroneous risk numbers. It took us weeks to find out what happened, which in trading terms is a lifetime. Now, it turns out in our original system, there was an algorithm buried deep in the code stack, which would multiply our output by -1, programmed by a developer who was long gone, with no supporting documentation to explain why it was there. But that's the nature of enterprise computing. You may have started with a clean and simple pipeline to solve a particular problem, but as your business grows, so does the complexity. With too many moving parts and technologies and a bloated code base, it becomes almost impossible to explain how and why your system works the way it does. The key problem here is that there's no visibility into what's going on, or more specifically, no data or analytics lineage to simplify troubleshooting and to help developers explain the output that they're actually seeing. When you add to that the constant need to re engineer pipelines to scale to growing business demands, you're inevitably left with a situation where it's extremely difficult and expensive to deliver data insights quickly. Now, we used to call this setup the 80/20 rule because engineers spent 80% of their time on managing lineage and scalability related issues and only 20% on actually building models and solving business problems. At Julius Technologies, we're helping companies reverse that ratio. We offer a low code solution for building and managing data analytics pipelines via graph computing that supports lineage and auto scaling out of the box. So, how's this possible? We combine the best of Julia and its high performance with the transparency and lineage of graph computing and a low code framework that enables easy graph creation and auto scaling. The net result is a truly revolutionary solution for building enterprise scale data analytics pipelines. Let's be clear about what we mean by graph computing. Graph computing is a powerful technology that allows organizations to build complex pipelines as a directed acyclic graph, or DAG. A DAG is a generic representation of any kind of computing, which is fundamentally just a collection of data transformations. Any computation, from the simplest formula to the most complex enterprise systems, can be reduced to a DAG. But the takeaway here is that DAGs are a perfect representation for building generic solutions to lineage and scaling challenges because they natively track all the data and analytical dependencies. The graph computing in itself isn't enough. Traditional graph solutions are difficult to use and adapt. They require a great deal of coding and are often limited in terms of their scalability. At Julius, we created a low code framework that makes it easy for developers to define and create sophisticated graphs, and also automates and optimizes difficult tasks like distribution and resource management. As a result, Julius graphs are simple to build and extremely fast and scalable, ideal for handling real world problems. So let's talk about performance. Here we see the results of a benchmark study showing how Julius is 10 to 1,000 times faster than the leading alternatives. You can see as the graph size increases up to 500,000 nodes, the competing platforms hit their limits, whereas it takes Julius only 15 seconds to run on a single computer. You can test these results for yourself on our developer environment, which is free for developers to sign up and use. So now let's go through a few applications of Julius using real world examples. So the first example we're going to show is an accurate reproduction of a bank's ML pipeline for credit approval. Here on the screen, we're showing the process for a couple applying for a credit line increase. So here you can see the entire machine learning training application from beginning to end, from the raw data to feature engineering, the training of the model, and then using the model for inference and reporting the final results. The graph representation is very intuitive. Here, the different colored nodes represent different physical machines. The workload in this case is automatically distributed to four different boxes. So, for example, all the yellow nodes are executed by the same physical machine. Now, let's look at how this application works. In the beginning, this is the raw data, which can be retrieved from any data source. That could be a relational database, public URL, unstructured. We have connectors from many different data sources, but developers are free to build their own as well. Then we can do a quick visualization of the data. We see a histogram here, but we can also measure for completeness and data quality. And then downstream, we can click on any node and visualize the data as of that point in the process. If we look at this node, we've added a few additional columns to the initial data. For example, one of the columns is called liar, which tracks whether or not certain conditions have been met on the initial application. If these constraints are broken, it means the applicant has lied on their application form. And down the road, we're training a decision tree model, which is a standard model sourced from an existing Python library. So one key point here is that no matter what analytics library you have, we can easily interface and source them from either your proprietary library or third party or open source library. All of that can be easily plugged in. That includes libraries written in C++, Java, R, .NET, and of course, Julia. So in this case, we're using a mature Python library to build the decision tree, and you can even drill down to visualize what the category decision tree looks like. As you can see, it's just a very typical tree that branches out using different attributes, and eventually in the leaf node, you're getting the default probability forecast for all the entries that fall into that bucket. So it's very intuitive to visualize how the logic works. For example, we can easily see that the most important attribute to look at is whether this couple is married, and you can follow the logic forward. Going back to the top level, the reason we have a multi-level display is to allow you to drill down to the smallest details if you want to see how something works internally, but also have the benefit to visualize an uncluttered top level to get an overview of the process and to navigate the graph. Further up the graph, we have the forecast of the default probabilities, and we have the various metrics for accuracy. For example, here we show the ROC curves and accuracy rate with different views. Now here, we also integrated the model documentation process into the same pipeline. So a developer can describe the corresponding data and analytics for any node, and with a single click, we can generate the entire end-to-end documentation with the actual live data populated. Changing the pipeline in this case will change the corresponding documentation automatically. So this is really useful for governance and control by automating most of the manual labor involved. So this is a self-contained application that highlights a few key benefits that Julius offers. The first is that a graph provides for complete transparency and lineage. For any node, you can just click and get the data and analytical logic behind the calculation, which makes the pipeline much easier to support and debug. For example, you can see what calculations go into any particular node. You can see the complete lineage, and you can also show the dependencies. What are the downstream dependencies that are derived from this particular data point? Making scenario analysis much easier because whenever you change any of the inputs, you don't have to recompute the entire graph. You can just compute those dependent nodes. So scenario analysis becomes much faster. So that's one benefit from having complete lineage and visibility, fast scenario analysis, which comes from using a DAG. So the second benefit is the auto-scaling capabilities. For this pipeline to scale, the developer doesn't have to write even a single line of code. Julius automatically takes care of scaling, and you can see that the distribution of the nodes is intelligent. It's not distributed randomly. For example, this cluster of nodes are all distributed to the same machine in order to minimize the network traffic, which is critical to performance. The third benefit I want to highlight is the low code aspect. So, to define this entire application, 63 nodes and rather complicated logic, a developer only needs to write 33 lines of declarations in our low code DSL. So, just to be clear, this 33 lines of code defines the pipeline with all the connections and dependencies. So, in terms of what's happening at the individual node, each node can call any complex function, and that function can be sourced from any library. You can even mix and match libraries in different languages within the same pipeline. Now, the difficult or time consuming part of pipeline building is the process of stitching these functions together, managing the memory, the hierarchies, distribution, etc. Julius takes care of all of that for you, so you only need to define or declare your pipeline using our low code syntax. The pipeline is then built automatically without much additional work on the developer side. So I know there's quite a bit of information being thrown your way, but if you want to do a deeper dive into the low code DSL with some specific applications and examples, we hosted a workshop earlier in the conference, which is accessible on YouTube. So let's move on to the final example, which is based on a much bigger graph that shows the scalability needed to run a bank's risk process. In this case, we're looking at valuing a portfolio of 100,000 trades. So while this graph is rather large with more than a million nodes, it certainly doesn't represent the limit. Julius can routinely handle graphs with hundreds of millions of nodes in a distributed manner. In this case, since the graph is so large, it can't be displayed on a single page, but we can still easily navigate the graph. Here we can drill down into the hierarchy of the graph to look at the individual trades and see all of the intermediate steps and how the calculations have been automatically distributed across multiple machines. We also natively support AAD, or adjoint algorithmic differentiation, out of the box, which is useful for financial risk modeling and also backpropagation for ML and deep learning applications. It's a powerful feature that provides for extremely quick sensitivity calculations and for computing gradients. Again, I just want to quickly highlight that to get all these benefits with a very large graph, a developer only needs to write 69 lines of code in our DSL to build this entire pipeline with over 1 million nodes. In practice, the equivalent system at a bank would comprise hundreds of thousands of lines of code or more. So these examples only scratch the surface of what Julius can do. You can appreciate how much faster and easier it is to build data analytics because we automate most of the difficult and tedious tasks. Julius can also be used to refactor existing pipelines in a piecemeal way to be scalable and transparent. So one of the reasons we started Julius was to offer Julia developers better tools for solving enterprise problems. The powerful combination of Julia and Julia's low-code auto-scaling graphs produces next-generation capabilities and speed. We're helping Julia developers build enterprise solutions in a fraction of the cost and time. Our low-code framework is based on Julia syntax, so it's easy for Julia developers to learn and use. And finally, we provide a viable migration path to Julia by allowing organizations to move in a piecemeal fashion without having to recreate their environments or code libraries from scratch. So we appreciate the opportunity to present to JuliaCon. We're excited to work with this community, and we're huge believers in the future of Julia and graph computing. Thank you for listening.